This webcast talks about how to quantify mechanical energy, meaning now we're going to learn how to calculate specific amounts of each type of energy. So we are still talking about mechanical types of energy, which would be gravitational potential energy, elastic potential energy, kinetic energy, and dissipated energy. So first, let's talk about gravitational potential energy, or EG. We recognize when there is gravitational potential energy because something in the system has an elevated position, a height above the ground. And here are the formulas for calculating gravitational potential energy. Notice in this table, it's giving you two versions of the equation. On the left, it says here's a snapshot of gravitational energy at a specific moment in time. And that says the gravitational energy equals the mass of the object multiplied by g multiplied by the height. G here is the acceleration due to gravity. And near Earth, that's always 9.8 meters per second squared. The mass is the mass in kilograms, and the h is the height in meters. Okay, so mgh is the way to calculate the amount of gravitational potential energy at a specific point in time. There's also a formula for the change in EG. We won't use this nearly as much, but sometimes, maybe someone climbs a tall mountain and we say, what was their change in gravitational potential energy? In that case, we take their weight, which is their mass times 9.8, and we multiply it by the change in their height. And the change in height is always the final height minus the initial height. Let's go to Worksheet 6F and calculate some gravitational potential energies. In the first problem here, we are considering exactly the same scenario, which is that a notebook, a binder, is sitting on a table. And so I'm going to draw that for A, B, and C. So, the notebook and the table are in exactly the same position in all of them. The thing that is changing from one to the other is the place where we are defining our zero reference level for gravitational potential energy. Usually, we set the ground as the point where we say EG is 0. But, so if we set the ground, the floor, as where the height is 0, then this book is actually on the table, so it's above that. So the book's height, the book's position, is 0.68 meters. Right, because the book is above the floor. And so then we could say, okay, so right now, the gravitational potential energy of the book is its mass times g times h. Well, the mass is 3 kilograms, g is 9.8, and the height is 0.68 meters above the ground. And so right now it has a gravitational potential energy of 19.992 joules. Thank you. What if, instead of defining the floor as where h is 0, we said, oh, the table, that's where I'm going to say the height is 0. And, we could really do this. A lot of our experiments, we put equipment on a table, and as long as the height doesn't change, we don't talk about how gravitational potential energy changes. And so in this case, with the table defined as our 0 reference level, well, the book has a height of 0. right? It's on the table. It's at the same level where we are defining h to be 0. And so we'd say, oh, well, right now it doesn't have any gravitational potential energy. And then there's one more example in C. So again, it's the same table, it's the same book, but it's just where we're defining height to be 0. Now we're saying, oh, the ceiling, that's where I'm going to say the height is 0. And since the book is below the ceiling, it's 2.5 meters below, so the book's height would be negative 2.5 meters relative to where we've defined 0. So now, in that situation, the gravitational potential energy of the book would be its mass times 9.8 times negative 2.5. So it is possible to have a negative gravitational potential energy. So here that would be negative 73.5 joules. You know, so if someone dug a tunnel under the ground, you know, you might have a negative height. It does happen. It may not happen too much, but just to be aware of it. In this next example, it's talking about the change in gravitational energy of a squirrel. So this would be an opportunity to use the change formula. The change in the gravitational potential energy of the squirrel is the weight of the squirrel, right? That's the mass times 9.8, multiplied by the change in height, which is the final height minus the initial height. Okay, so the squirrel has a mass of 3 kilograms, G is 9.8, the final height is 2, the initial height is 50. And so here we're going to get a negative change in EG because the squirrel has less gravitational potential energy as he comes to a lower branch. And so it's going to be negative 1,411.2 joules as he comes down from that very tall branch to one that's lower. Okay, I'm going to go back to the slides on quantitative energy conservation. And now let's talk about elastic potential energy. So remember that elastic potential energy is, you recognize that when there's something in your system that has the property of being elastic. That means that you can stretch it or compress it, you know, somehow change its shape, but when you remove your hand, it will go back to its original shape. So it's a reversible deformation. Okay, so things that have that ability to be deformed, but then they'll pop back to their original shape, they are able to store elastic potential energy. The most common example is a spring. Okay, and so here are the equations for calculating elastic potential energy. So the snapshot formula, and that's the one that is the most commonly used, it says, okay, elastic potential energy equals 1/2 of the spring constant K multiplied by the displacement of the spring squared. So in order to use this formula, be sure that the K, the spring constant that you put in, has units of newtons per meter, and the displacement has to be measured in units of meters. It's very common for a problem to give you a displacement in centimeters, and you will have to convert those into meters before you use this equation. There's also an equation for the change in elastic potential energy, but we don't use that very often, and so I'm not going to talk about that right now. You could always say that the change in elastic potential energy equals the final elastic potential energy minus the initial elastic potential energy, and you could use that snapshot formula to calculate both of them. Okay, let's go back to the worksheet and we'll go down to number 6 and use that elastic potential energy formula. So here they're treating a bungee cord kind of like a spring. They're giving us a spring constant even, right, of 140 newtons per meter, and they're telling us that the bungee cord has been stretched by 25 meters. And they're asking how much energy is stored. So we're talking about elastic potential energy, and the formula is 1/2 multiplied by the spring constant K and multiplied by the displacement squared. And as I plug in, I just want to make sure that everything is in standard units. So they gave me the K, the spring constant, in newtons per meter. So that's good. I don't need to convert. And here they gave me the displacement in meters. So I don't need to convert that either. Remember to square the displacement. And so here we get an amount of 43,750 joules. Big number. Let's look at number 7 as well. Just do one more of these. Here it says how much energy is stored when a railroad car spring is compressed by 10 centimeters. So I need to convert this. 10 centimeters is 0.1 meters, right? 10 divided by 100 is 0.1 meters. Notice they did not give me a spring constant, but they do give me some more information. They say the spring requires about 10,000 newtons of force to be compressed 3 centimeters. Well, that reminds me of the formula that tells me how much force has to be applied to stretch a spring, right? The applied force equals the spring constant multiplied by the displacement. So they're saying that 10,000 newtons causes the spring to be compressed by 3 centimeters, right? That 3 centimeters is 0.03 meters. Make sure you convert. And so then, if I divide both sides by 0.03, I get that K is 333,333 newtons per meter. Okay, so now we've found K. We can use that to answer the original question, which said how much energy is stored. So that's talking about elastic potential energy, which is 1/2 times that spring constant times the displacement squared. So we found the spring constant to be 333,333. They're talking about a displacement of 10 centimeters, which is 0.1 meters, and I have to square that. And so the elastic potential energy would be (1,667 joules. Okay, I'm going to go back to the slides because now we need to talk about kinetic energy, which is energy that we recognize because something is moving. Okay, and here we go. Here's the equation to calculate kinetic energy. EK, kinetic energy, is 1/2 times the mass times the velocity squared. Mass has to be in kilograms. Velocity has to be in meters per second. Okay, so let's go calculate or use that equation in some problems. So number 3, back in worksheet 6F, we've got how much kinetic energy does a big SUV traveling at 70 miles per hour have? Well, I want to use this formula, right? The kinetic energy is half of the mass times the velocity squared, but I'm noticing that they gave me the velocity in miles per hour. That's not standard metric units. So I need to convert that. So 70 miles per hour. I know that 1 mile is 1609.34 meters. This was an approximation. Okay, and I know that 1 hour is 3,600 seconds. And so that is a velocity of 31.293 meters per second. Okay, so I can find the kinetic energy of this SUV. It's half of its mass multiplied by its velocity squared. Which is very big. It's 979,234 joules. Okay, let's do one more here. How fast does a 50-gram arrow have to travel to have 40 joules of kinetic energy? So it's talking about energy, so I'm going to use the kinetic energy formula, which is that kinetic energy is half of the mass multiplied by the velocity squared. And here I'm going to be solving for the velocity. So they're telling me that the kinetic energy is going to be 40 joules. Now be careful, 50 grams is not a standard unit. I need to convert to kilograms. So it takes 1,000 grams to equal 1 kilogram. And so that would be 0.05 kilograms. And I need to put in the mass in kilograms in this formula. And then I'm just going to solve for the velocity. So the velocity would be the square root of 40 divided by 1/2 and divided by 0.05. Which would be which would be 40. Okay. And I'll do one more here just to finish this page, the change in kinetic energy. So this one is talking about a change in kinetic energy. So that would be the change in kinetic energy formula, which is half of the mass multiplied by the final velocity squared minus the initial velocity squared. Notice the way I'm writing this. I'm squaring each of these velocities before I subtract them, okay? And then we have one other issue. We've got megagrams, not kilograms. So let's go convert that. I need to take the megagrams to kilograms. I know that mega means 10 to the 6th grams, right? That would get rid of the megagrams. But then I've got grams, not kilograms. So I then need to go from grams to kilograms. And I know 1 kilogram is 10 to the 3rd grams. And so this would be 14,000 kilograms. 14,000 kilograms. Okay. So I've got half of 14,000. And I have to take the final velocity, which was 8, and square it. And then I subtract the initial velocity squared. And this is huge. I get negative 5,040,000 joules. Okay.